On today's episode, we're unboxing the new iPhone. All right, so wait, no, where'd I put it? Crap. All right, so today we're going to talk about chemical reactions and stuff. No, wait, where are you going? Stop. No, wait, what? So, anyway, oh, you're still here. So, thank you. Screw that other guy. All right. So, hi. So yeah, today we're going to talk about some solution stoichiometry for the General 1 folks. And we'll do some equilibrium stuff for General 2 if you haven't already skipped ahead. If you haven't, hey, how you doing? Remember all this stuff? Man, it takes you back, doesn't it? But last episode, if you saw that, I did a little bit of stoichiometry, kind of covered that again. And because it's really important this time of the semester. But today we're going to do solution stoichiometry, which is just really stoichiometry with one more unit conversion thrown in the mix. When we started stoichiometry in whatever chapter you do stoichiometry, chapter 3 or 4, whatever it is. For me, it's 4. We really do stoichiometry with just 2 conversion factors, gram to mole conversions and your mole to mole conversions. Once we get into the next chapter where we're talking about aqueous solutions, we throw one more into the mix. But it's still the same stoichiometry, same conversion math we've been doing since the start of the semester. We just added one little, we've gone from 2 to just 3. But it's just 3 is all it is. So let's start by kind of reminding you how molarity works. Remember, molarity is, oops, that's not it. I was rehearsing and I forgot to restart. I didn't really rehearse. I was just going through the slides and seeing where I screwed up. There we go. So molarity is moles of solute per liters of solution. And in General 1, usually the solute is just some solid you've dissolved in water because water is usually our solvent. So moles of the solid you've mixed in the water per the volume of the solution. And the volume has to be in liters. Again, all this is a concentration term. It's just the one chemists like to use. In the real world, quote unquote, a lot of times you measure things with percentages. Chemists like molarity because it has that mole unit worked into it. Because we can use it in a really similar way that we use molar mass. Remember in the chapter before, or last week, or the last episode, however you're doing this stuff, we saw how molar mass can be used to convert between grams and moles. Molar mass kind of does a similar thing. It allows us to go from liters to moles, or vice versa. So take this reaction between silver nitrate and sodium chloride. And let's see how many grams of silver chloride we can make, starting with a half liter of 1.25 molar silver nitrate. So it's the same setup as any stoichiometry problem. You know, convert this much of this chemical to this much of this other chemical based on this given chemical reaction. And remember, the first step for any stoichiometry problem is to take what's given and convert it to moles. So here we're given a volume of a known concentration and molarity. So we'll start with the volume. And remember, 1.25 molar is 1.25 moles per liter. That's how we define molarity. Moles of solute, liter of solution. So if we use that as a conversion factor and set it up this way, the liter unit drops out. And now we're in moles of what's given, just like we were last week. So the next step of any stoichiometry problem is to convert moles of what's given to moles of what you want. So if we look at the chemical equation, it's a 1-to-1 relationship. For every 1 silver nitrate, we're going to produce 1 silver chloride. So we can use that to convert to moles of silver chloride. And from there, it depends on what unit is asking you to find. Here, we're looking for grams. So again, anytime you want to go between grams and moles is molar mass. And that gives us 89.6 grams of silver chloride. So look at another example. And here we'll look at sulfuric acid reacting with sodium hydroxide. which hopefully a lot of you guys by now recognize as a acid-base neutralization reaction. This one, if we didn't mention, that's a precipitation reaction because there's your solid. But that's another topic. But let's say you're trying to figure out how many milliliters of 3 molar sulfuric acid you'll need to neutralize 50 milliliters of sodium hydroxide, and the sodium hydroxide is 2 molar. So again, same setup as the last stoichiometry problem and any one that I did on any other episode. Convert this much of to this much. When you're converting between one chemical and another, that's stoichiometry. Again, the first step is to take what's given and convert it to moles. So we're given 50 mils, although we do have to convert it to liters. I'll save that step just to save me some space on the screen. But mils to liters, most people can do that okay. Again, we can use the given molarity to convert between liters, convert liters to moles. And just like the last example, and really any stoichiometry problem, the middle step is always the same. You do that mole to mole conversion based on the given equation. And according to this equation, is for every 1 sulfuric acid, we need 2 sodium hydroxides. So that's our conversion factor here. And now we're in moles of sulfuric acid. All right, this time we're asking for a volume of a certain concentration. So again, remember, molarity means moles per liter. So a 3 molar solution would be 3 moles per liter. Or if you flip it around where the liter term is on top, the mole unit drops out. And now we can calculate an answer in liters, which we can do a liter to milliliter conversion, again, like we did back in the first chapter. So it looks like we need 17 milliliters to do that conversion. So a couple things to keep in mind. Again, it's the same. It's always the same setup. This convert this chemical to this chemical. Given this reaction. But it's you always go through the same kind of steps. Some people like to make little block diagrams to kind of show how you to go through it, but I hate doing those because they'll try to memorize the diagrams, figuring out what they did. And I can tell, which leads me to my next point. Yeah, I can tell when people are just kind of trying to do things, but they don't really get what they're doing. Because in a problem like the last one we did, you'll notice there was no molar mass that we plugged in anywhere, like we did in the first problem. The reason we do that, or we didn't, is because we weren't doing anything with masses. We weren't given a mass that we had to convert to moles, like we did in the last episode's examples, and we didn't in that first problem we did today. So unless you're having to convert grams to moles or moles to grams, anything with a mass, then you don't need molar mass, at least in a stoichiometry problem. The only thing stoichiometry is good for is getting you between grams and moles. And if you don't have any masses you need to work with, you're not going to use it probably. So yeah, I can see that when sometimes people, they'll just say, okay, I need molar mass somewhere because, we talked about it in class. Maybe I'll put it here. I don't know what I'm doing. So again, just treat it like a unit conversion problem. And if you're still stuck on the conversion math, setting everything up the way it should, for everything to cancel out, you need to go back and review the chapter 1 conversion math. Because if you can do those problems, you can do the ones in these last couple of chapters, because again, we're only using 3 conversion factors, grams to moles, liters to moles, and moles to moles. Moles of what's given to moles of what you want. So more stoichiometry, maybe next time. I mean, I might as well do gas stoichiometry next time. Maybe, we'll see. But moving on to the general 2, guys. For General 2, this is the time of the semester where you start to look at equilibrium. And for me, I always call equilibrium the stoichiometry of General 2 because, stoichiometry, once you start it in General 1, it just keeps going on. Like every chapter, we introduce something until maybe, I don't know, we start talking about electron configurations in chapter 7 or 8 or something, depending on what book you use. And for equilibrium, it's almost worse, because once we start talking about equilibrium, we pretty much talk about it for the rest of the semester. It comes up at some point, except maybe the last chapter. You know, for us, we end with nuclear chem, so there's no equilibrium there really. But so I'll getting a little tongue-tied. But I don't know what that was. But I figured we'd start with just a kind of a intro to what equilibrium is. And the next time we'll do a little more with actual calculations. So to start with, we start by going back to something we talked about in the previous chapter with kinetics, because the two are tied together. And you know, in the kinetics chapter, you learned about energy diagrams. And you take a simple A, B gives you C, D reaction. The energy diagram for that might look something like this. So you start with your two reactants, A and B, and if they collide with enough energy, they might make it over this activation energy hump to give you your two products. But unless you're actually devise some way to siphon off your products, which sometimes you can do that depending on the reaction, if your C and D is, you know, building up inside your beaker or flask, whatever you're doing the reaction is in, eventually you're going to build up enough C and D where they're going to collide with each other as everybody's kind of swimming around the same pool. And if they collide with enough energy to make it back over the hump, you can remake your products. And for a system like this, notice it's actually easier going back the other way. So once that starts to happen, you'll eventually reach a point where both reactions are occurring basically simultaneously or at the same rate. You know, every time the forward reaction is occurring, the reverse reaction is occurring somewhere else in that system. And that's when you get a chemical equilibrium. Equilibrium, remember, the equal means equal rates. They don't have to be the same amount or anything else. Equal means equal rates for chemical equilibrium. So again, that just means that, you know, whenever A and B is colliding, somewhere else in that same pool of chemicals, C and D is colliding to give you A and B. You know, forward reaction and the reverse reaction, they're occurring at the same rate. So instead of writing both reactions, we'll usually use our double arrow. And it really doesn't matter what you write as the reactants, but usually what you actually start with, the things you're actually mixing together in your beaker or flask or whatever you're using, that's what you write on the reactant side, like you normally would. So again, kind of like we talked about in chapter 1, you know, when people first made this observation that this equilibrium thing exists, they started to study it. And that can lead to, these observations can lead to laws. And a scientific law that was made after observing chemical equilibrium was the law of mass action, which basically says if you have an equation with this generic formula, A and B give you C and D, capital is the chemical, lowercase is the coefficient. When it reaches equilibrium, you'll have this thing called the equilibrium constant, which is basically the ratio of the concentration of C and D, or your reactants, over your products, A and B in this case. And each concentration is raised to a power that's equal to their respective coefficients. So it's not like the rate law stuff in the kinetics chapter where, you know, the orders had to be chemically, or had to be derived from the initial rate method or something else. Here with the equilibrium constant, I mean, it comes straight from the chemical equation. So, for example, if you have the reaction NO2 going to form N2O4, just to kind of let you see what I mean by this, you can start the reaction at different concentrations. You can start with your reactant, you can start with your product, a mixture of the two, and it's going to eventually reach a chemical equilibrium because that's how equilibrium works. Eventually, both are going to start to react in both directions at the same rate. So let's say at these different concentrations, when you reach equilibrium, these are the concentrations you get for your reactant and product. And again, you'll notice it's not the same concentrations every time. It does depend on the concentrations you start with, but no matter what you start with, it's going to reach equilibrium. And these are the concentrations for the equilibrium, when equilibrium is reached in each of these three trials. So if you just take just a straight ratio, you divide the product concentration over the reactant's concentration for each of these three trials, you'll notice you get a different ratio. But if you factor in the stoichiometry, where the fact that it's actually two NO2s on the left side, so if you make that NO2 squared, again, raise each one to a power equal to its coefficient, then it becomes a constant value, no matter what the equilibrium concentrations are. All right, so that's how the law of mass action works. There's just something going on where this chemical system is the happiest, if you want to be anthropomorphic, when it reaches this magic ratio. Now, one other thing to kind of add as far as how the equilibrium constant works is going back, or actually I'm jumping ahead, sorry. But I might have been able to save myself if I hadn't just flubbed and admitted that I screwed up. But try it again. So a couple of things to mention about the equilibrium constant. One of the things that it can tell us is which side of the equilibrium is favored. So if you have a equilibrium constant that's greater than 1, we call that a product favored system. And basically what that means is that when you reach equilibrium, you have a greater concentration of products than you do reactants. So it looks like the forward direction is the favored direction, because when you obtain equilibrium, you end up with a greater amount of product. Again, both are present no matter what you started with, but when it's a product favored system, you tend to have more product at equilibrium. On the other hand, if you end up with an equilibrium constant that's less than 1, we call that a reactant favored system, which I made a cut and paste error there, didn't I? I wonder if I can fix that live so I don't have to start over for that silly thing, reactant favored. Hey, there we go. I didn't capitalize, but I don't care. Because going back to what we said about how we define the equilibrium constant, it's just a ratio of product over reactant. I mean, we factor in stoichiometry, but at the end of the day, it is a ratio of product over reactant. So if you have a product favored system, if the forward direction is the one that's favored, you should have more product at the end, and so this ratio should be bigger than 1. If the reverse direction is the one that's favored, that means you have you're going to have a greater concentration of reactant once you reach equilibrium. So the bottom part's bigger than the top part, which means you're going to be less than 1. So like I like to say, don't let the chemistry throw you. This is just ratio talk. That's all we're doing. All we talking about is ratios. So, and that comes into play when we do other stuff later on in the semester. But one other thing to mention just in general is going back to, and this is what I meant to say a minute ago, going back to this generic equation and the equilibrium constant, that ratio, there it is. Okay, I had it flipped. This expression is true for, it's only true for chemicals that are in the aqueous or gas phase. If it's anything in a solid or a liquid phase, we don't factor into our expression of K. So for example, let's say in this equation, B and D were aqueous phase, A was a gas, but C was a solid phase. when our expression for the equilibrium constant wouldn't include C, because solids and liquids aren't factored into your expression of K, only aqueous or gas phase chemicals. And the reason for that is that the concentrations of solids and liquid substances don't really change. Now, aqueous concentrations can change as you add or take away solvent, or add more solute, take away more solute. And something similar can happen with things in the gas phase, because you can compress or expand volumes. But in the solid phase or liquid phase, as you add or take away more of that solid, the concentration per se doesn't really change. So let me show you what I mean. Say you have sodium chloride. You look up the density of solid sodium chloride, it's about 2.2 grams per milliliter. So that means a liter of this salt is about 2.2 kilograms, which converts to 36 moles. So if you wanted to show this as a molarity, moles per liter, it would be 36 moles per liter, or 36 molar. If you had twice as much sodium chloride, you would have 72 moles, and a 2-liter sample of your solid. Again, we're talking about a hunk of solid, not a solution. So you'd have that many moles per 2 liters. That's still 36 molar. So again, the concentrations of solid and liquid phase chemicals stay constant. So we don't bother factoring it into the expression of K. And there's other ways to kind of describe it. And you say, well, that constant's actually factored into something else. I just like to keep it plain and simple and say, just don't, solids and liquids, you don't include them in your K equation. All right. Finally, one other thing. You'll notice that the little C here, which I didn't mention before, C stands for concentration, because we're talking about concentration. You'll sometimes see a little EQ for equilibrium, although I don't like that. It's a little vague, especially in General 2. For a nursing chem lower level, might be okay. But in General 2, we also talk about how you can measure the equilibrium constant with respect to pressure. And it's the same basic expression, the same basic equation. You're just, instead of having a ratio of concentrations, you have a ratio of pressures, or partial pressures. And the idea of raising everybody equal to their coefficients, that's still true. So a lot of times we'll have a little P for pressure and a C for concentration, just so you know which of the two types of equilibrium constants we're talking about. And if you want to convert between the two, you can use this little equation here, where R is your gas constant, like we've seen a lot in the last semester and a half. And we use the version, the 0.08206 version that we were first introduced, not the other one with the joule unit. T is temperature in Kelvin, like it usually is. And delta N, again, the delta means final minus initial, your change. N means moles, but specifically in this case, it means moles of gas. So the difference in moles, final minus initial, product minus reactant. How is the moles of gas change during the reaction? So in our reaction here between NO2 and N2O4, let's say that 216 value, that's at 298 Kelvin, which I think it is in real life, but don't hold me to it if that's not true. Our delta N, we have 1 mole of gas on the left, 2 on the right, so our delta N there is -1. If you plug those into our Kp equation here, along with our gas constant, you get a equilibrium constant with respect to pressure of 8.83. But the real sort of trick to this equation, the thing you really have to remember is delta N means, it's moles of gas. Most people remember that it's moles, but it's specifically moles of gas. So if you take this example, converting carbon and carbon dioxide to carbon monoxide, let's say the Kc, the equilibrium constant with respect to concentration, is this guy at 345 Kelvin. If you wanted to convert that to a Kp, here the delta N is 2 minus 1. You get 2 moles of gas on the right, only 1 mole on the left. Remember, the solid doesn't count. So the delta N here is 1. So you plug those values into our Kp to Kc conversion equation, along with the gas constant. You get a Kp of 9.3 times 10 to the 5. So a couple other things to kind of mention as far as the equilibrium constant goes. For starters, you notice I didn't include units with the equilibrium constant, either one of them. That's because the units depend on the overall stoichiometry of the equation, which we kind of saw with the rate constant in the kinetics. We kind of ignored the units of the rate constant most of the time. We do the same thing with the units of the equilibrium constant, just for more or less the same reasons. Also, too, for our Kp, the equilibrium constant with respect to pressure, I mentioned that with Kc, it was only aqueous or gas phase stuff, because those are the only two things that affect concentration, not solid or liquid phases, as we saw with our sodium chloride example. With Kp, though, I should point out, you're only plugging in the partial pressures of your gases, which most people do without thinking about it. But yeah, the Kp would only be with respect for gases, because that's the only time we really measure pressures. Pressures of solutions and solids and liquids, they don't really change. But that's one thing to keep in mind with Kp if you ever work with it. It's your ratio of partial pressures, but only gases. Kc, which is what most people work with in Gen Chem. Again, it's only solid, or it's not solid. It's gas or aqueous phases only. If it's a solid or a liquid phase, we don't bother including that in our expression of Kc. All right. And that'll become important as we start to do some other stuff with equilibrium and the equilibrium constants. And oh yeah, one more other thing. If you go back and look at those last two problems where I did the Kp to Kc conversion, you will notice that whether you wrote it as a Kp or a Kc, both numbers, they were still, actually both examples, they were both product favored, because they were both bigger than 1. I should have made one less than 1, but oh well. Notice when you converted it to a Kp, the number was different, but it was still telling you the same information. They were both bigger than 1. So no matter whether you're looking at the Kc or the Kp, they can both tell you which side is favored, which again is a little thing that we use when we're doing some other stuff later on in this chapter and some of the ones that follow. Because again, equilibrium is not going away not anytime soon. So that's it for this week. Unless you're watching the next video right away, thanks. Keep on going. But unless I haven't recorded it yet, in that case, you're just gonna have to wait a week. You're probably not. You're probably watching this a lot later. Maybe, I don't know. But I'm babbling again, so I'm going to shut up and I'll see you next time.